So, good evening everybody. This is the ABC of stellar evolution. As you can see from the subtitle, it's a look at the birth and the life and the death of stars. And along the way, we'll see where all of the elements in the periodic table have come from. Excuse me. There we go. So, birth, life and death. And we're going to start with looking at what's going on in the centre of a star and asking, how do stars ignite? Where do they come from in the first place? And then we'll consider the balance that keeps all stars doing what they do, shining as well as producing elements. We'll think about how the mass of a star affects its life, and we'll ask what happens when the fuel runs out. And that's where we introduce the idea of stars being fusion factories that generate all the elements that we see around us in the Earth's crust. Star death. How do stars die? Well, they might go out with a bang, they might go out with a whimper. What's left afterwards? We'll see what the remnants of a dead star look like, and the last of that will be, if gravity wins in the end, we'll just touch on black holes. So let's just remind ourselves about the Sun. So here's a time scale. The Big Bang is on the left there at 0. There's a completely separate talk about what happened at the Big Bang and how the Big Bang generated all of the hydrogen that's throughout the universe. It took about 3 minutes to generate shed loads of hydrogen, which is essentially the starting point of this particular talk. So we are now at 13.8 billion years since the Big Bang. And our Sun is middle-aged, meaning it was born something like 9, maybe 9.5 billion years after the Big Bang. We'll see how in just a minute. And the Sun is now about halfway through its stable life. I say stable life because after about 10 billion years from its birth, the Sun is going to change. So the Sun is in the stable phase of its life, which is just as well because, of course, life has evolved on Earth over the last 2, 3, 4 billion years or so, and hopefully with a bit of luck it might continue to do so for quite a few billion years on. But once the Sun is about 10 billion years old, the Sun will change for reasons we're going to explore shortly. The Sun is going to expand and will become a red giant, and after it's been a red giant it'll probably blow off the outer layers of the star, and the Sun will then end up as a very small and compact white dwarf star. So that's an indication of the timeline. These sizes are not to scale. The timing is roughly to scale, but the sizes are not supposed to be to scale. Again, we'll see relative sizes shortly. So that's just to give us a little bit of context. The Sun is a fairly average star, and so using that as a baseline is not a bad idea. So what's going on in the heart of a star? I'm not going to convert this into a nuclear physics talk. So we know that at the heart of a star we have nuclear fusion. In the case of our Sun, hydrogen is being fused into helium and releasing energy. So what's going in is 4 hydrogens, or 4 protons, because the nucleus of the hydrogen atom is just a single proton. 4 protons are being fused together and you end up with the nucleus of a helium atom, and helium is 2 protons and 2 neutrons. So we don't really have to worry about the details. All we care about is nuclear fusion, input 4 protons, output 1 helium nucleus, and in converting 2 protons into 2 neutrons, other stuff is released. There might be some electrons flying off, there might be some neutrinos, but all we care about is that there is a mass difference between the left-hand side and the right-hand side, and that mass difference is what is converted into energy, which allows the Sun to shine. In each second of the Sun's life, it's taking roughly 600 million tons of hydrogen and converting it into 596 million tons of helium. And that missing 4 million tons is what gives us the energy. That's the energy release. So stars are not just nature's way of lighting up the universe, they are the fusion factories that make the elements heavier than hydrogen. Yes, you can ask, where does the hydrogen come from? But that's not the focus of this particular talk. We're talking about stellar evolution. So we're assuming that we start with bucket loads of hydrogen, more than enough for our purposes. And if you do want to know the answer to that question, that's a different talk. So we're starting with hydrogen. So we can ask the question, right, where do stars come from? Well, actually, anybody can make a star. It's quite easy. You can make a star in just 5 steps. What you do with step 1 is start with a very big cloud of hydrogen. Number 2, you wait. Number 3, you wait some more. Step number 4, wait just a little bit longer. And then by step 5, you've got a star. That's all you need. Start with a large amount of hydrogen and a fair bit of patience, and you'll end up with a star. Gravity will do its stuff if you wait long enough. So making stars is easy, and that's where they're made, in large hydrogen clouds such as this particular nebula. This is the Great Nebula in Orion that some of you might have seen if you are interested in amateur astronomy. It's visible to the naked eye, but this is a Hubble picture showing exquisite detail. And one thing we can notice is that it's predominantly pink, because hydrogen has a particular transition line in the red, and hence clouds of hydrogen tend to glow pink. So we can ask the question, if we've got a large cloud of hydrogen, what triggers star formation? Well, roaming around the galaxy are so-called giant molecular clouds. And why are they called giant molecular clouds? Well, for 3 good reasons. 1, they look like clouds, a bit like the picture we just saw. Secondly, they consist mainly hydrogen molecules. And you can see where I'm going with this. The 3rd reason they're called giant molecular clouds is because they're big. They could be many dozens or maybe 100 light years across. Remember that the distance between any 2 stars is likely to be a few light years. The nearest star to our Sun is about 4 light years away. So a 100 light year diameter cloud encompasses a very large number of stars. So you might imagine that when a cloud that large collapses, it doesn't just generate 1 star, it generates many stars. Perhaps dozens, perhaps hundreds, maybe even thousands of stars are generated by the collapse of a hydrogen cloud. What makes one of these giant molecular clouds collapse? There are a number of things that could trigger the collapse. One could be one cloud collides with another. These clouds are just going around, circling around the Milky Way galaxy, just like the Sun and the solar system are orbiting the centre of our galaxy over a period of a few 100 million years or so. So these clouds are doing the same, and every once in a while one cloud might collide with another, and that might trigger the start of star formation. It's also possible that shock waves moving through the cloud could trigger star formation. What could possibly produce a shock wave? Well, we're getting a little bit ahead of ourselves, but perhaps the death of a star that collapses and ends up as a supernova, can produce shock waves that would then go rippling through a cloud and could then trigger the next generation of star formation. And finally, one thing that we know triggers star formation is the collision of galaxies. We can see where the hydrogen clouds are and where star formation is rife. Remember the picture of the Great Nebula in Orion? It looked predominantly pink. So these little knots of pink here that you can see in the spiral arms of this galaxy, these are star-forming regions. And if we look at here the Whirlpool galaxy, we can see it's interacting with this presumably little satellite galaxy on the side there, and it's producing a large amount of pink, especially on this side, but also in the other spiral arms. And it's thought to be the interaction of the big galaxy with the smaller galaxy that's perturbing, gravitationally speaking, the spiral arms and forming a lot of star formation in these pink regions. And if we look at galaxies in collision, here we see 2 galaxies colliding, and the tidal effects, the gravitational effects of one galaxy getting close to the other, is producing these long tidal tails that you can see, which give this galaxy pair its characteristic name of the antenna or antennae galaxy. But if we look more closely with the Hubble Space Telescope at what's going on inside that red box, we realise again there's a huge amount of pink here, there's a very large amount of dust in these two galaxies, and there's also a very large amount of new stars being formed as these galaxies pass through each other. We should remember that even though there might be a fraction of a trillion stars in any two galaxies that collide, the likelihood of two stars hitting each other is actually quite remote because of their separation. So when galaxies pass through each other, they gravitationally interact, and that's what perturbs the gas. And the gas clouds of one galaxy will collide with the gas clouds of another, so lots of atoms and lots of molecules will bang into each other, even if the stars don't. So, in other words, we could probably survive quite happily if our galaxy collided with another one. That's going to happen before too long. The Andromeda galaxy is going to collide with the Milky Way galaxy, but it's unlikely that our sun will actually hit anything, but it is likely that a lot of the hydrogen gas in both galaxies is going to be triggered into new star formation. Let's have a look at how one of these molecular clouds collapses. This might look like a star. This is actually a large cloud of hydrogen in a simulation. We haven't got the patience to watch a hydrogen cloud and wait for a few million years to see what it does. So we put this into a computer, and here the University of Exeter has done a simulation where they started with a large cloud of hydrogen, and they're going to let it go and let gravity do its stuff. Before letting it go, to make sure that it's relatively realistic, what they've done is apply a few random fluctuations. Every point in this cloud is given a tiny nudge in a random direction and a small random velocity so that it collapses in a relatively realistic state. So we can then ask the computer to do its stuff, calculate all of the gravitational interactions between each point in this cloud and every other point in the cloud, and then we just see how it runs as a function of time. So let's do that and see what happens. Some parts of the cloud might be too far from the centre and they might be given a nudge that allows them to escape, but most of the cloud is collapsing under gravity, and the yellow there is higher temperatures and higher pressures as the cloud is collapsing. We can zoom in a little bit to see what's going on. Eventually, the pressures and temperatures will be high enough for nuclear fusion to take place. Eventually, the nuclei of the hydrogen are close enough that they can fuse to make helium. And so stars are born. You can see that if we wait long enough, it ends up looking like a popcorn machine. There are so many stars generated by this large cloud, it looks like thousands of stars are being generated. Most of them are staying fairly close to where they were born, but notice that some stars are gravitationally interacting with other stars, and some might get thrown out of this particular star cluster. Our sun appears to be on its own, but presumably it was born in pretty much this sort of way and was probably one of those stars that got thrown out of a cluster. We can't tell which one. If we look into our environment, we can't tell which cluster we came from because it was simply too long ago, being 5 billion years. This sort of three-dimensional spin here gives you an idea of what the cloud might look like when it's done. You notice that most of the cloud has been depleted. There's still some hydrogen around, but most of the hydrogen has been condensed into the core to make this cluster of stars. So if that's what the simulation says, if we start with hydrogen and put in some gravity and then run the simulation for a few million years, that's what we might predict. Is that what a star cluster actually looks like? If we image star clusters, we might not see the hydrogen, but when we look at star clusters, we do indeed see something that bears some relationship to what we saw in that previous simulation. So maybe we've got the physics of star formation about right. Ultimately, every star is a question of balance. Gravity is trying to pull the star in, and the fusion going on at the core of a star is producing radiation, and that radiation is trying to get out of the star, and as it travels from the core to the surface, it exerts a pressure which, if it counteracts gravity, means the star is in balance. If the two opposing forces, gravity compressing the star, radiation trying to expand the star, if they're in balance, then we have a happy star that's in equilibrium. If they get out of balance, if for any reason gravity and radiation are out of balance, then the star must evolve. That is the driving force of stellar evolution. As long as you have gravity and radiation balancing, the star is happy and stable, just like our sun has been for billions of years and will be for billions of years. But if gravity and radiation get out of balance, the star must evolve. And indeed, many aspects of star birth, star life and star death can be thought of in terms of that balance and what I like to think of as the ABC of stellar evolution. So let's look at the ABC. There's 3 bits of relatively simple physics that you need to understand in order to understand star evolution. First, we've already said that if we want to get energy out, we need to fuse things together, whether they be protons in the case of the nuclei of hydrogen, or multiple objects, which are collections of protons and neutrons in the case of helium nuclei. But always they're positively charged. So if you want to fuse these together, first you have to overcome the fact that they are positively charged and so will be trying to repel each other. Like charges repel, and so 2 positive charges don't like to be pushed together. So if you can get the temperature high enough, if you can get the density high enough and raise the temperature and raise the pressure and get these particles close enough together, you can accelerate the fusion process. So that's the A of ABC. If you can raise the temperature, you can accelerate fusion. B, we've already looked at that, that's balance. If gravity and radiation are in balance, the star is stable and in equilibrium. And finally, compression produces heat. If you take, well, you know that from pumping up a bicycle tyre. If you compress the air in a tyre, the air and the tyre and the pump all get hot. Well, a star is basically just a ball of gas, so the same thermodynamics applies. If you compress a star, then it'll produce heat and the temperature at the core of the star will go up. So that's really all you need to know, A, B and C. If you can get things hot, you can accelerate fusion. Balance is always a balance between gravity and radiation, and compression produces heat. That's the only physics that you really need to know to understand how and why stars evolve. Let's just remind ourselves how astronomers catalogue stars. So stars are often drawn on this so-called Hertzsprung-Russell diagram, or HR diagram, in which the position of a star is given by its surface temperature, not the core temperature where fusion is taking place, but the surface temperature from relatively cold at a few thousand Kelvin to quite hot, a few tens of thousands of Kelvin. And on the vertical scale we have luminosity, from very dim stars to very bright stars. There's our sun, roughly near the middle. Our sun is very average, and we tend to measure luminosity in terms of how luminous compared to the sun. So by definition, the sun has a luminosity of 1. And the sun's surface temperature is a little bit under 6,000 Kelvin. At the top of this diagram we have giant stars or supergiant stars. At the bottom of the diagram we have some dwarf stars, and we'll see when we talk about particular types of star where they occur on this diagram. Live fast, die young. Mass affects how a star lives and how a star evolves. Stars of different mass follow quite different lives. If we think about a high mass star, and again we're really talking about relative to our sun, so not something the mass of our sun, but something 10 or 20 or 30 times higher than that. A high mass star has a lot of fuel, so naively you might say there's an awful lot of fuel there for it to burn, so presumably it burns for quite a long time. Well, actually it's the opposite. Gravitational forces are of course very strong if there's a large amount of mass there, and if the gravitational forces are strong, that means you have to generate a huge amount of energy to prop the star up, to keep the star in balance. That means the nuclear fuel must be used at a prodigious rate in order to keep that star in balance. So although there is a lot of fuel there, it has to burn it really fast to keep the star stable. So rather than living for perhaps billions of years like our sun, a high mass star, much more massive than our sun, might only live for millions of years rather than billions of years. And as you would understand on geological timescales, if a star only lives for a few million years, you haven't got time to make a load of planets and then have a whole load of life evolve. So having a star that's stable for billions of years is quite important for us. If we turn that around and ask what happens if we have a low mass star, well, again, naively you might say, well, there isn't much fuel there, so maybe they don't last very long. Well, it's the opposite. Gravitational forces are relatively weak. If we have a star, for instance, one that's much less massive than our Sun, the gravitational forces are weak, and therefore the radiation forces that are required to balance the gravity are, again, relatively low, and you don't need to burn your fuel very rapidly. Hence, although you don't start with that much fuel, your fuel actually lasts a long time. For instance, if we have stars of mass, let's say 10% of the mass of our Sun, we're not actually sure what happens when the fuel runs out because it's never actually happened. The lifetime of these stars can be much, much, much longer than the age of the universe. The universe is only 14 billion years old. And if you make a low mass star, it might live for 1 trillion years, or at least many, many, many billions of years. And therefore, these stars haven't died yet, simply because their lifetimes are so long. So we can speculate as to what would happen with a low mass star, but we've never actually seen one die yet. But we assume that it's live fast, die young, and we also assume that it's live slow, die very old. I've talked about mass, and it's mass that determines how a star evolves. But as a little bit of an aside, let's just think about the size of a star. The mass of a star tends to be fairly close to the mass of our Sun. It can be smaller by a factor of 10 or maybe 100, and it can be larger by a factor of 10 or maybe 100. But the sizes can vary by quite a lot more than that. So as a little bit of an aside, although it's not strictly relevant to star evolution, let's just ask ourselves what sort of size stars can we have. Let's start with something we're all familiar with, including that planet on the right-hand side there. These are the planets not in order of distance from the Sun, but the planets in order of size. Mercury, Mars, Venus, and then a very similar sized Earth. If we take Earth from the right and put it onto the left of the next panel for comparison, there's Earth in the bottom left-hand corner. And we can see that's a fair bit smaller than the ice giants Neptune and Uranus, and considerably smaller than the gas giants of Saturn and Jupiter. Let's do that same trick again. Let's take Jupiter and put it on the left-hand side of a panel, and then start looking at the relative sizes of stars. Notice that Jupiter is not that much smaller than one of the smallest stars we know of, Wolf 359. I'm sure you know that if you're a Star Trek fan. So there's a star which is not that much bigger than Jupiter, which is why sometimes Jupiter is thought of as almost a failed star. Jupiter's core is quite hot. If Jupiter was more massive, the core of Jupiter might be just about hot enough to undergo thermonuclear fusion. So there's a small star, and there's our Sun for comparison, some 10 times bigger in terms of diameter compared to Jupiter. And there's Sirius, one of the brightest stars, well, the brightest star in the sky apart from the Sun itself, and you can see that's quite large compared to our Sun. Let's do the same trick, put Sirius in the left and then look at other stars. We see that compared to Sirius, there are some stars around that are absolutely huge. These are the red giant stars. Pollux in the constellation of Gemini, Arcturus and Aldebaran. These stars are red enough to actually show a red colour when you look at them in the night sky. But we're not done yet. Let's take that red giant Aldebaran, put it on the left-hand side, and now we see we're getting ridiculous sizes. That, remember, is a giant compared to our Sun, and now we have Rigel, Antares and Betelgeuse. Betelgeuse that you may have heard of recently, undergoing a little bit of a variation in brightness, and people are speculating whether or not that's close to the end of its life, and maybe one day Betelgeuse will go supernova. Not quite the biggest star we know of. Remember, these stars are similar in mass. They might vary by 1 or 2 orders of magnitude in mass from our Sun, but if they are so huge, that must mean that they are very low density. But we're not quite done, because people have found a few stars that are even larger than Betelgeuse. So there's Betelgeuse on the left, and then we're getting into silly names now. But if we look at the star on the right, the wonderful name of VY Canis Majoris, that is one of the largest stars known. I think in the last couple of years they found a slightly larger one by 10 or 20% or so, but still that is a giant by any measure. And just, it doesn't really make much sense, but I'll do it anyway. Let's just compare the size of the Sun to the size of the largest star that we had there. So there's the Sun, and now I'm going to show you the size of VY Canis Majoris. And if you can't see it on the right hand side, let me bring it in. There it is. Okay, you can see just about from the curve there what the size of that star would be. I admit this is a slight exaggeration. I haven't exaggerated the size of the red supergiant. I've actually exaggerated the size of the Sun. If the Sun was actually truly to scale with this giant, then the Sun would be barely 1 pixel on the screen that you're looking at and would be almost invisible. So sizes vary enormously, even though masses tend to only vary by 1 or 2 orders of magnitude. Okay, so here's the interesting question. What happens when the fuel runs out? It's not going to happen with our Sun just yet. We hope we're good for another 5 billion years or so, but the question is raised, what happens when the fuel runs out? One thing to remember is that when we're talking about burning, people often talk about burning, but not burning in the sense of oxidation, burning in the sense of nuclear burning, nuclear fusion. It's still called nuclear burning for some archaic reasons. When we're talking about nuclear fusion, not much of the star's mass is actually used up. So even though our Sun is producing a huge amount of energy over 10 billion years, that doesn't mean it's getting smaller and smaller and shriveling up and there's going to be almost nothing left by 10 billion years time. No, what we're saying is that, remember the numbers, 600 or so million tons of hydrogen every second is converted to 596 million tons of helium, and that 4 million, that 0.5% or so, is the mass that's lost and converted into energy, and that's what produces the visible and the infrared and all the other electromagnetic energy that comes out of the Sun. Even after billions of years, only 0.5% is lost. 99+% of the original mass is still there. It's simply been changed from hydrogen into helium. So in terms of a fuel reserve, after 10 billion years, we've barely touched the fuel reserve. It's pretty much all still sitting there. So what happens when the hydrogen runs out? Well, that's why we have the ABC of stellar evolution. With the ABC, we can get a handle on what's going to happen when the Sun comes to the end of its life. When the hydrogen runs out, or strictly speaking, when the hydrogen starts to run out, when most of the fuel has been used, the radiation at the core will start to drop. And if the radiation starts to drop, that means the star gets out of balance, because normally gravity balances radiation. If the radiation drops, gravity now beats radiation. So if gravity is beating the radiation, what's going to happen? The star shrinks, and compression produces heat, and that heats the core to a higher temperature. So we are now in a situation where the core, we've taken most of our hydrogen, converted it into helium. The hydrogen is now running out. If we compress the core, we're going to compress the helium. What happens? It forces the nuclei together, these nuclei that really don't want to get close. The nuclei of helium are 2 protons and 2 neutrons in each nucleus. They've got twice as much charge as a single proton, so getting them close is even more difficult than getting hydrogen close to another hydrogen nucleus. But if you heat the core enough, you can accelerate the fusion of helium. So forcing the nuclei together accelerates the fusion of helium into still heavier elements. And once that happens, you generate more radiation, and then radiation will then get back into balance with gravity. Balance is restored, equilibrium is restored. So stars are self-regulating objects. Well, they have to be really, otherwise they would all be runaway nuclear reactions. So having converted hydrogen into helium, the star must change, but it will change in such a way that it can then start fusing helium into heavier elements. And then you can then ask the question, well, how long will this continue? Surely helium will be used up, but does that mean we go back to the start of this little loop again? If the helium's used up, does that mean gravity beats radiation? Balance is disrupted, so the star will compress, it'll accelerate the fusion of the next set of elements until balance is restored. How many times can you go through this loop of fusing heavier and heavier elements together to build up all of the elements in the periodic table? We have to think about nuclear stability. So here's a graph of nuclear mass running from left to right. So hydrogen is on the left and the heavier elements are on the right. And nuclear energy, I'm not going to talk about how we measure that or what the units are. All that matters is if we do experiments on Earth, we can work out how much energy it takes to make a particular nucleus out of its constituents. Or if you prefer, if you start with a nucleus, how much energy does it need to take those constituents apart? All we really need to know as far as stellar evolution is concerned is that if we start, let's say at the left-hand side there with hydrogen at nuclear mass of 1, just a single proton, if we take 4 lots of hydrogen and make it into helium, or perhaps we should say, let's take 1 kilogram of hydrogen and make it into approximately 1 kilogram of helium. If we start with hydrogen and make helium, the amount of energy we get out of that is dependent on the vertical distance between these 2 red dots. Helium is a long way above hydrogen on this nuclear energy scale. So that means if we take a kilogram of hydrogen, convert it into a kilogram of helium, we get a lot of energy out. If we then start with a kilogram of helium and make it into heavier elements, for instance, if we take helium and compress helium together to make carbon, well, yes, we still get energy out, but notice that the curve is starting to bend over, which means we don't get as much energy out. For every kilogram of fuel that we put in, we don't get as many joules of energy out in the process, even though we're, again, starting with about a kilogram of fuel. And if we keep on going and say, what if we were able to take a kilogram of carbon and fuse carbon nuclei together into heavier elements, well, each time we do that, we get a little bit less bangs for our buck. Every kilogram of fuel we use gets us less energy out. And if we fuse neon into silicon, we get a little bit. And if we fuse silicon into iron, we get just a little bit. But iron, you notice, is at the top of that curve. I'm not going to talk in detail as to why, but iron nucleus is a very stable nucleus, and if we fuse elements together up to iron, energy is released. But beyond iron, that curve is now dropping, which means if we wanted to fuse iron together to make silver or gold, we're on the downhill slope. We can't get energy out that way. We have to put energy into the system in order to convince iron to fuse into heavier elements to make, for instance, silver and gold. They're just picked at random as 2 elements in the periodic table. So we can understand the generation of all the elements up to iron, but then when it comes to heavier stuff, we sort of say, well, what we've said up till now, let's just fuse hydrogen, and then when we're done, fuse helium, and then when we're done, fuse carbon. That only works up to this magic element of iron. Once a star has produced iron, it's in trouble, because it can't simply continue fusing to generate energy to keep itself in balance. But the other consequence of that particular curve is the fact that this slope, remember I said you get less bangs for your buck each time. Let's just imagine hypothetically we are trying to go from hydrogen all the way down to iron. I'm picking a few elements along the way. It doesn't matter the fact that I'm not choosing every element. If you generate carbon, you'll also generate elements on the way between helium and carbon. And similarly, from carbon to neon, you will generate elements on the way from carbon to neon. But these are the sort of milestones, if you like, of fusion. If we start with a large, massive star and convert hydrogen into helium, then that fuel might last for many millions of years. And remember, once it's used up all the hydrogen, we've got essentially the same mass of fuel, but if we now want to burn helium in order to make carbon, the same amount of fuel is not going to produce the same number of joules unless we burn it really quickly. If we want to keep that star in balance, we're going to have to burn that helium into carbon very quickly in order to give us the same amount of energy that's going to balance the gravity trying to crush this star, simply because we get less joules for every kilogram of fuel that we use. So when it comes to converting helium into carbon, that same amount of fuel is not going to last many millions of years. It might only last, let's say, 500,000 years. And then if we want to start fusing carbon, if the star is big enough and we're capable of crushing it down and start fusing carbon into heavier elements, the fuel is not going to last as long because less bangs for our buck. It's going to have to burn more fuel per second in order to generate the same number of joules per second to balance the gravity. So burning carbon to produce neon might only last 5,000 years. And similarly, going down the next step, the fuel, the same amount of fuel, might only last 10 years. And burning oxygen to make silicon might only last 5 years. And when it comes to right at the top of that curve, if we've got a star that's big enough to make all of the elements up to iron, the last stage where we're fusing silicon into iron might only last days. Even though we're talking about the same amount of fuel. 10 to the power, who knows, 10 to the power 30 kilograms would last millions of years if we're burning hydrogen, but would barely last a week if we were burning silicon and fusing silicon to make iron. So you can see that each of these cycles is not equal in the sense that they don't have the same length of time. When it comes to the end of a star's life in terms of getting to iron, it's going to be more and more and more rapid. There's an avalanche effect, and it is catastrophically fast by the time it gets to the end of its life. So here's the familiar periodic table of the elements with our friend Mendeleev in the middle there. Let's just dim out some of the boring detail. We know that hydrogen in the top left there is made in the Big Bang, and we're not talking about its origin. The Big Bang also makes helium up in the top right there, but we are talking about stars that take hydrogen and make helium, fuse helium. There's actually quite a lot of helium already around, floating around the universe, because it was made in the Big Bang. But in that sense, it doesn't take much of a role because it's mainly hydrogen that collapses in these clouds, and it's mainly hydrogen that is the first step in the fusion process. But there is lots of helium around anyway. Stars, although they are fusion factories, haven't actually contributed that much to the total amount of helium in the universe. Most of the helium in the universe is primordial. It was made in the Big Bang, and stars have only added a tiny amount on top of that. But if hydrogen is made into helium, and then helium is made into carbon, and then we have neon and oxygen and silicon all the way up to iron. As I've said, I've only looked at a few milestone elements. I'm not filling in the gaps. If we can make silicon, then we can make all of the elements up to silicon. If you make silicon, it might well be radioactive and decay into lighter elements. The point is, how do we progress up the periodic table? Once we've reached iron there in red, iron, element number 26, we're barely 1/3 of the way through the periodic table. But we look around the Earth's crust and we go around with our little hammers and we start looking at what the world is made of. We find that the world is made of all of these elements up to element 92 or so. So where does this heavy stuff come from? How can we go beyond iron if no star can fuse elements and release energy any further than iron? We have to ask the question, how do we get to cobalt, nickel, copper, zinc, blah, blah, blah? How do we get silver? How do we get gold? So the fundamental question is, why does gold exist? If it's not made by the process that I've described so far, then how can we explain the existence of gold in the Earth's crust, amongst all of the other heavy elements? I'm just taking that as one example. So what we've said so far is that we can fuse, or burn if you prefer, hydrogen to helium, and then helium to carbon, and then carbon to neon, and then blah, 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 all the way up to iron. But iron does not release energy if you fuse it. It needs an input of energy. So where do the heavy elements come from? Well, the bottom line is star life cannot answer that question. We have to look beyond the cycles that are going on within a living star, and we have to look at how stars die. For a medium mass star, so medium in this context means something not dissimilar to the mass of our Sun, not particularly heavy, not particularly light, but something around the mass of our Sun, gravity may not be strong enough to hold on to the outer layers of the star when helium starts to burn. We've run out of hydrogen, the star is going to compress, it's out of balance, so it compresses, compression produces heat, heat produces fusion of the helium. When that helium starts to ignite and generate radiation, it might be that the gravity of the star is simply not enough to hold on to the outer layers of the star, and effectively the burning helium can blast the outer layers of the star off into interstellar space. The star expands and the outer layers cool and redden, and the star then becomes a red giant. If it expands, it cools, just like any other gas. If you compress it, it heats. If you expand it, it cools. And that's when we get the phase of a red giant. Let me just remind you where the red giants are. They're on the right-hand side because they're redder with a lower surface temperature because they're cooler. But they're more luminous, they're above the Sun in terms of luminosity, not because they're hotter, au contraire, they are actually cooler, but they are more luminous simply because they have a much larger surface area. And it's just Stefan's law, take a large surface area and emit a little bit of light from every square meter. If you have a very large area, you're going to have a more luminous star. So that's a red giant. When the radiation from the core is puffing out the red giant and pushing the outer layers out, in some cases those outer layers can be lost completely. Not just puffed out to make the star rather bigger, but gravitationally completely released from the star and blasted away to form a so-called planetary nebula. The word there is misleading. Planetary is nothing to do with planets. It's simply called planetary nebula because when they were first observed, they looked a little bit like planets in the sky. If you blast away the outer part of a red giant star, what are you left with? Well, the very hot core is what we call a white dwarf, and those white dwarfs are down here at the bottom of the table. They're quite hot because they were the core of a star, not just the surface temperature we're talking about. They were much hotter. And they're over on the left because they're quite hot, and they're quite low down on this diagram because they're quite small, and so the opposite argument to the red giant. Although they're quite hot, they have a relatively small surface area, and hence they are not particularly luminous. But the reactions are no longer going on in this star. It no longer has the gravity, it no longer has the outer part of the star, that's all been blown away. Gravity is no longer crushing this star and producing the heat required for nuclear fusion, so this is really just a hot object which is doing nothing other than sitting there slowly cooling off. So a white dwarf, if you wait long enough, will simply get dimmer and dimmer and dimmer as it radiates heat and slowly loses its internal heat, and its temperature will start to drop. That's what the outer atmosphere might look like once the star has blown the outer atmosphere away. That's why they were called planetary nebula, because in a small telescope you might confuse that with the appearance of a planet. This one is beautifully spherical and slightly translucent. You can see some stars perhaps through it as well as some stars in front of it. Not all planetary nebula are anything like as symmetrical as that, because stars are usually spinning, and depending on how fast they're spinning, when they cast off the outer atmosphere of the star, they can produce all sorts of complex structures. So this particular planetary nebula is called the Cat's Eye Nebula, and you can see it's got a very complex structure, which is presumably the result of the way the star was spinning as the outer part of the atmosphere was thrown off. That's one of my favourite planetary nebula. That's visible from the UK, low down in the south during the summer months, the so-called Helix Nebula. And again, you get a beautiful indication of how the atmosphere has been thrown off by the central star, which is the white dwarf right in the middle there, that has thrown off most of its outer atmosphere and left a rather compact object in the centre there. By compact, I mean that this white dwarf might be, roughly speaking, the size of the Earth, not the size of the Sun or any of these huge red giants we've seen before, but the white dwarf itself will be only 10 or 20,000 kilometres or so in diameter. The actual outer atmosphere could be light years in size as this outer atmosphere slowly moves into interstellar space. This one actually is so large, even though it's quite a distance away, on the sky it appears to be about half the size of the full moon. It's not particularly bright, but it is huge in its angular size, giving you an idea of just how large these outer atmospheres can be when they form planetary nebula. That's what might happen to a star like our Sun. It could end up as a red giant, and perhaps that red giant could end up as a planetary nebula, and the Sun ends up as a white dwarf. But if the mass of the star is high enough, then the gravity can actually hang on to those outer atmospheres. It doesn't lose the outer atmosphere. If the mass is large enough, it can keep the star's integrity together, and not only does hydrogen burn to helium and helium to carbon, if the mass is high enough, it can keep that integrity, and when the helium runs out, it can start burning carbon. When the carbon runs out, it can start burning neon. If the mass is large enough, this cycle will continue many, many times before you end up at iron. And you end up with a sort of an onion, if you like, of different elements, because not all of the hydrogen is used up before the helium starts burning, not all of the helium is used up before the carbon starts burning. You end up with shells of the different elements. So you can see a high mass star is actually a hodgepodge of quite a large number of elements, all the way from hydrogen up to iron. At the end of its life, if it's a high mass star, once it started to produce iron, remember, it's got nowhere else to go. It can't start fusing iron. So once the silicon starts to run out, what can a star do? The iron can no longer provide the energy to support the star, so once the silicon has run out and all you've got left in the core is iron, then gravity wins and the star will collapse. The core will collapse in perhaps a matter of seconds, and then the rest of the star will fall on top of it. The collapse will crush the core down to only a few kilometers, and the shock wave that results will rebound and will effectively eject everything else above the core into interstellar space. And that's when we get the familiar supernova explosion. This is an image taken by the Hubble Space Telescope of the Crab Nebula, a supernova remnant that was seen in the skies of Earth in 1054 AD. So it was seen 1,000 years ago. It went off, of course, earlier than that because it's taken light time to reach us. If we think about the amount of energy, we can do a very quick back-of-the-envelope calculation to work out, if you've got a star of a given mass, how much energy would it take to simply separate all of its components to infinity. A simple energy argument tells you that you need an energy of something like 10 to the power 44 joules in order to rip a star apart, which is what happens during a supernova. So that's how much energy is released in a supernova. And to give it scale, if you imagine the total energy output of the Sun, not just the tiny fraction that the Earth receives, if you think of the total energy output of the Sun, which is sending electromagnetic radiation off in all 4 pi directions, if you think of that amount of energy every second for the entire 10 billion year lifetime of the Sun, that adds up to about 10 to the 44 joules. In other words, if you take the total energy output of the Sun over its entire lifetime, But imagine releasing that in just a few seconds, then you realise the scale of a supernova explosion. Shouldn't really call it an explosion. It isn't, strictly speaking, an explosion. And of course, the word explosion just isn't big enough to encompass the sheer scale of the energy release. And it is precisely that energy release that fuses the heavier elements. A star on its own can't fuse iron and generate energy, but once a star has gone supernova, there is energy to spare, because the supernova itself has generated enough energy to start fusing iron into pretty much everything else for the rest of the periodic table, and a whole load of unstable elements that will eventually decay back to a lot of the elements between iron and what we see now, the top of the periodic table around uranium. So all of the elements that are in, remember that Russian doll, that onion of all the elements from hydrogen to iron, all of those are ejected into interstellar space, and a whole load of new elements are made at the same time. So the heavy metals that we find, the heavy elements that we find on Earth, were probably made in a supernova, which means the Sun cannot be a first generation star. The Sun cannot be simply made of the hydrogen cloud. It must have been made of elements that we see in the Earth, which means there must have been a supernova that preceded the Sun's existence. It is thought that maybe the Sun is certainly not first generation, maybe the Sun is perhaps fifth generation. In other words, in the early universe, a cloud of hydrogen produced a whole load of stars. Some of those stars were massive, some of them only lived for a few million years. They went supernova and generated a few heavier elements, and dispersed some of those heavy elements back into the interstellar medium, so the next hydrogen cloud that collapsed had a little sprinkling of heavier elements in it, and then that went supernova and enriched the cloud with a few more elements, and that happened again and again and again, and by the time the Sun came along, by the time the cloud that would ultimately produce the Sun started to collapse, that was enriched with a number of different elements as well as hydrogen producing the fuel for the Sun, and the various heavy elements ending up in some of the planets that ended up orbiting around the Sun. So we don't know what star that was. We have no way of telling what unknown star in the past existed before our Sun. That was too long ago. If our Sun is 5 billion years old or so, then we're talking about stars that lived and died many, many billions of years ago. But they must have seeded our local region of space with those heavy elements for us to see around us today. One sobering thought is just to remind ourselves that atoms, they're essentially immortal, in the sense that hydrogen was made in the Big Bang and you effectively can't do much with a proton, therefore hydrogen is going to be around forever. But it's also true of many of the heavy elements as well. So we like to think of us being, well, I'm made of a certain number of atoms, but actually I'm just the custodian of the atoms that I'm using at the moment. They were made in a star that died in a supernova and redistributed the atoms throughout space. I'm using these atoms for a little while, hopefully for a few more decades yet, and in a few billion years our Sun will die and those atoms will be recycled back into space for another generation to use. So atoms go round and round this cosmic cycle probably many, many, many times. So we don't necessarily think of atoms as being indestructible, but in this sort of sense they are. Once they're made, there's not much you can do to destroy an atom of iron, other than put it into another supernova and turn it into something else perhaps. So this is an idea of how nucleosynthesis works. This is our best guess as to where the elements come from. So we know that most of hydrogen and helium at the top of there are made in the Big Bang. So again, I'm not talking about primordial Big Bang hydrogen. Let's assume that we're starting with hydrogen. Where do most of the other elements get made? Well, some of the lighter elements get made because of cosmic rays. We believe very energetic cosmic rays can form the lighter elements, lithium and beryllium. But you notice that most of the other elements from carbon onwards are made in either small stars or large stars. And a lot of the heavier elements like gold or lead, they are probably made in supernova, as I've described. I'm being a little bit cagey saying probably, because in recent years some people have speculated that if certain stars collide with each other, which is possible, recent experiments have indicated that black holes collide with each other and neutron stars collide with each other. It's thought that they may be energetic enough to make some of these heavier elements as well. So although in the past it was assumed that only a supernova can make these heavy elements, it is now thought that maybe there are other mechanisms, but that's the one I'm sticking to just for the time being. After a supernova has crushed the star's core and ripped off the outer part and sent that off into interstellar space, what is left of the star's core? Remember, we're talking about a very massive star which has crushed the core, and then the rebound has sent everything out into space. But what does the star's core look like? Well, it's smaller even than a white dwarf, which is only 10,000 kilometers or so in diameter. A tiny star is the result of what happens in a supernova. It might only be a few kilometers in diameter, maybe 10 kilometers radius or maybe 20 kilometers or so in diameter. It's what we call a neutron star. Very dense, because effectively what we've done is taken atomic nuclei and forced them together. The protons have changed to neutrons, so what we end up with is a soup which is essentially just neutrons. The neutrons don't want to get any closer than basically touching, and therefore what we've got is you don't any longer have the idea of atoms with a nucleus and an electron buzzing around it. You now have just an entire soup of pure neutrons. So the density of a neutron star is essentially the density of an atomic nucleus, so very, very much higher than ordinary matter. It also might have a very strong magnetic field and be spinning very quickly, just like the conservation of angular momentum says that an ice skater pulling their arms in will spin much faster. The same conservation of angular momentum from a large star spinning quite slowly. Once you've crushed it down, it will now be a small star spinning very rapidly. And this can give rise to radio emissions, which are then periodic and give rise to pulsars, pulsing radio sources. Rather interestingly, I thought, it's not known, but it is thought that a neutron star is effectively just a messy liquid of individual neutrons floating around inside this object, which is of order 10 or so kilometers in size. But it's thought that maybe it's got a liquid core, but arguably a solid crust, which I thought was quite interesting. How do they know it's got a solid crust? Well, because if they listen to the periodic pulses that pulsars produce, they can know what those pulses are very accurately. And if they watch them for long enough, they notice that pulsars tend to produce very regular ticks, and then occasionally they glitch, and suddenly the pulse period changes, perhaps only in the 10th or the 9th decimal place. But there is a noticeable jump, because otherwise the period of rotation is very stable. They can notice tiny changes in the period. So they think it's the equivalent of an earthquake, a starquake if you like. The crust of a neutron star suddenly rearranges itself slightly. An earthquake on Earth might raise the seabed level by, what, meters or something when continental plates start to move. In the case of a neutron star, it might only change its radius by microns or something like that, but still it'll change its moment of inertia, and as a consequence it'll change its period of rotation, and that can be noticed. So the idea of a neutron star having star quakes I thought was a very interesting idea, and it's based on that sort of data that makes them think this model might be an indication of what a neutron star actually looks like. So neutron stars have a particular size characteristic, typically 10 kilometers or so, because that's the point at which a given number of neutrons will touch each other. And neutrons certainly do not want to get any closer, because once they start overlapping, once the wave function of two neutrons start to overlap, you get an exclusion principle similar to those of excuse me, electrons. But You can get them closer. They really don't want to overlap with each other, but if the star has enough mass in the first place, gravity will force them together whether they like it or not. They can object all they like, but if the gravity is strong enough, you can crush them together and the neutrons no longer have any identity. And if neutrons are not stopping it crushing any further, what is there that will stop it crushing down to smaller and smaller and smaller sizes? And the answer is we don't know of anything that can stop it crushing down once it's overcome the reluctance of neutrons to touch each other. And the result is the stuff of science fiction. A black hole, again, the topic of a different talk and not something I'm going to dwell on, but we know that if you can crush things down to a given radius for a mass of the mass of our sun, if you crush it down to just 3 kilometers, then the escape velocity goes higher than the speed of light, and then you end up with a region of space from which light cannot escape. And we have no real idea of what happens to the matter that ends up falling within that particular region, called the event horizon. We have no way of getting information out, so we can speculate about what might happen once the mass has shrunk down to less than 3 kilometers in the case of the mass of our sun, but we have no real idea of what's going on in there. We see some evidence for black holes, massive stars that have come to the end of their lives. The evidence is in the form, quite often, of a black hole that's feeding. In other words, if a black hole is one of a binary pair of stars, then if one of the stars turns into a black hole, then matter from the other star can get sucked off the star itself, effectively funneled off the star, and that matter can end up going down into the black hole, which is where the arrow is pointing there. So just like water can never go down the plug hole of a bath all at the same time, it tends to circulate and then go down the plug hole. The same is true of mass being ripped off a neighbouring star, trying to get down into the event horizon of the black hole. The conservation of angular momentum says that the matter will spiral around and will eventually get there, but on the way it will be heated up, and the region immediately around the black hole, which is usually an accretion disk as shown by this particular artist's impression, that region will get very hot and will radiate huge amounts of energy, all the way from radio waves all the way to X-rays, because of the sheer temperatures involved. So nothing is coming out of the black hole, but the region immediately around the black hole is going to be very energetic, very hot, and producing huge amount of energy. And that ultimately is what we think the fate of a very massive star will be, more massive than our sun. Our sun is not going to go that way. Our sun will probably end as a white dwarf, but if it was 10 times the mass, this might be its ultimate fate. So let me just recap first what I said about birth, life and death. We started with stellar nebula collapsing, and we thought about the fact that when we're trying to balance gravity with the fusion radiation from the core, we have to worry about which particular elements are being fused, because once we get to iron, we have a problem. And for lightweight stars, we might simply produce a planetary nebula and blow off the outer atmosphere, but if it's a heavy star, we might end up with a supernova explosion, which will result in a neutron star or a black hole. Let me just try and summarize all of that rather more visually. We start with a cloud of mainly hydrogen, and that collapsing hydrogen, give it some gravity and just wait a while, you'll end up with some stars. If it happens to make a relatively small star like our sun, then our sun will live for billions of years, and at the end of its life will swell up into a red giant, and will probably, once the helium starts burning to make the heavier elements, it'll probably blow off its outer atmosphere and produce a planetary nebula. What's left will be a white dwarf, an object, roughly speaking, the size of the Earth. But that same cloud could also make a somewhat larger star if a larger clump happens to collapse and produce a lot of mass in the same volume. We end up with a larger star, which could end up puffing out into a red supergiant, and depending on the mass, if the mass is large enough, it can be going through the cycles of hydrogen to helium, helium to carbon, carbon to the heavier elements, etc., all the way up to iron, at which point it comes to a very abrupt stop and suddenly the whole thing collapses and you get the star crushed down to next to nothing, and 99% of the star, or at least a large fraction of the star, is blown away in a supernova explosion. What's left is either a neutron star or a black hole, depending on the details and perhaps the mass of the star that started it. But in both cases, regardless of whether we're dealing with small stars or large stars, and regardless of whether we end up with a white dwarf or a neutron star or a black hole, what's important is that a lot of the matter is recycled. A lot of the matter is blown off either as a planetary nebula or a somewhat more spectacular supernova explosion, but in both cases a lot of the matter is sent back into interstellar space and ends up reseeding molecular clouds, so that the next time the molecular cloud collapses, it's collapsing with, again, mainly hydrogen, but tiny amounts of the heavier elements, and each time you go through these cycles, regardless of whether it's a small star or a large star, each time you go through a new generation of stars, you're building up the amount of heavy elements. So if you look at how many heavy elements there are in a star, you get a good indication of its age, because you can tell whether it's first generation or second generation or third generation. And every generation of stars is contributing to all of the elements between hydrogen and iron, and if it's a particularly heavy star, it'll also be contributing to all of the elements from iron up to the end of the periodic table. So that's the ABC of stellar evolution. Those three factors, the A, the B and the C, can tell you pretty much everything you need to know to understand star life and star death and the origin of all the elements in the periodic table. Thank you much for listening.